Imagine standing on the surface of an alien world, looking up at a sky the color of burnt orange. Massive Saturn hangs overhead, its rings stretching across the horizon like a cosmic bridge to nowhere. The air is thick, thicker than Earth's, but you can't breathe it. The temperature is so cold that water becomes as hard as granite, and rivers flow with liquid methane instead. This isn't science fiction. This is Titan, Saturn's largest moon, and it may be humanity's greatest trap. Titan is the only moon in our solar system with a substantial atmosphere. It's larger than the planet Mercury and possesses lakes, rivers, and rain, just like Earth. For these reasons, scientists have long considered it one of the most promising destinations for human colonization beyond Mars. But there's something they don't often discuss in the glossy mission proposals and optimistic press releases. The astronauts who make that journey may never come home. Today, we're going to explore why the first humans to set foot on Titan will likely spend the rest of their lives there, not by choice, but by the cold, unforgiving mathematics of orbital mechanics, engineering limitations, and the staggering distances involved in deep space travel. Let's start with the journey itself, because understanding how impossibly far Titan is from Earth helps explain why returning would be nearly impossible. Titan orbits Saturn at an average distance of about 886 million miles from Earth. To put that in perspective, Mars at its closest approach is only about 34 million miles away. Titan is more than 26 times farther than Mars. The Voyager 1 spacecraft, travelling at about 38,000 miles per hour, took nearly 4 years just to reach Saturn after launching from Earth. Current propulsion technology would require a minimum of 7 years for a crewed mission to reach Titan, and that's with ideal launch windows and gravitational assists from other planets. Realistically, we're looking at 8 to 10 years of travel time. That's a decade of your life spent in a cramped spacecraft, breathing recycled air, eating freeze-dried food, and staring at the same walls day after day. But here's where the trap begins to close. That's just the one-way trip. A return journey would require another 7 to 10 years. Add in the time needed to conduct meaningful research on Titan's surface, let's say 2 to 3 years minimum, and you're looking at a total mission duration of 17 to 23 years. That's longer than most professional careers. Astronauts who left Earth in their 30s would return in their 50s, assuming they survived the journey at all. The psychological toll of such a mission cannot be overstated. The International Space Station, orbiting just 250 miles above Earth, has seen astronauts develop depression, anxiety, and interpersonal conflicts during missions lasting only 6 months. Now multiply that isolation by 40. Multiply that distance by 3.5 million. The human mind isn't built for such extremes. NASA and private space agencies know this. They've run the simulations, conducted the studies, and reviewed the proposals. And increasingly, the consensus among mission planners is becoming clear. The first mission to Titan may need to be one-way by design. Even if we could convince astronauts to spend 2 decades of their lives on this mission, there's a more fundamental problem: fuel. Getting to Titan requires an enormous amount of propellant. Chemical rockets operate on a principle called the Tsiolkovsky rocket equation, which basically states that the amount of fuel you need increases exponentially with the distance you want to travel and the mass you want to carry. To escape Earth's gravity, reach Saturn's orbit, and then slow down enough to land safely on Titan, you need a staggering amount of fuel. But here's the real problem: you'd need to carry all the fuel for the return journey with you from Earth. Think about what that means. Not only do you need fuel to get your crew and habitat to Titan, but you also need fuel to get your return vehicle to Titan, plus the fuel that return vehicle needs to get back to Earth. Each kilogram of return fuel you add requires additional fuel just to transport it there. It's a vicious cycle that quickly makes the mission mass spiral out of control. Let's put some numbers to this. The Saturn V rocket that sent Apollo astronauts to the moon weighed 6.2 million pounds at launch. About 85% of that weight was fuel. The moon is only 238,000 miles away. Titan is 886 million miles away, more than 3,700 times farther. While the exact scaling isn't linear due to gravitational assists and different orbital mechanics, the fundamental challenge remains. You'd need a launch vehicle orders of magnitude larger than anything humanity has ever built. Some proposals have suggested manufacturing fuel on Titan itself using local resources, a concept called in situ resource utilization. Titan's atmosphere is 98.4% nitrogen and 1.6% methane with traces of hydrogen. In theory, you could extract methane and combine it with oxygen to create rocket propellant. But here's the catch. Setting up a fuel production facility on Titan would require massive industrial equipment, power generation systems, and years of operation before enough fuel could be manufactured for a return trip. You'd essentially need to build a chemical processing plant on a world where the average temperature is minus 290 degrees Fahrenheit, where your equipment would be constantly bombarded by cosmic radiation, and where every component would need to function flawlessly with no possibility of resupply from Earth for nearly a decade. The energy requirements alone are staggering. Titan receives only 1% of the sunlight that Earth does, making solar power nearly useless. You'd need to bring nuclear reactors, multiple ones for redundancy, and enough fuel to run them for years. Each reactor adds thousands of pounds to your mission mass, which requires more fuel to transport, which requires a bigger rocket, which costs more money, which makes the mission less feasible. We're starting to see the trap form. The very things you need to escape Titan must be brought from Earth, but bringing them from Earth makes the mission so massive and expensive that it becomes practically impossible. Now let's talk about Titan's environment, because the temperature alone makes this world hostile to human life in ways that are difficult to overstate. Titan's surface temperature averages around minus 179 degrees Celsius or minus 290 degrees Fahrenheit. This is so cold that water ice becomes as hard as granite. Methane and ethane, which are gases on Earth, exist as liquids on Titan. The moon has lakes, seas and rivers of liquid methane and ethane, an entire hydrological cycle, just like Earth's water cycle, but with hydrocarbons instead. At these temperatures, materials behave in unexpected ways. Metals become brittle and can shatter under stress. Rubber and plastics lose their flexibility and crack. Electronics designed for Earth's temperature range may fail or behave unpredictably. Every seal, every gasket, and every moving part in your habitat and equipment must be engineered to withstand these extreme conditions for years without maintenance or replacement parts from Earth. Your habitat would require constant heating, which requires constant power. If your power generation fails, if your nuclear reactor has a problem, if your batteries degrade, if any part of your energy infrastructure breaks down, the cold will kill you in minutes. Your habitat would become a tomb of ice as the internal temperature rapidly equalizes with the external environment, but the cold creates another, more insidious problem. It makes Mars look like a tropical paradise by comparison. Mars has an average temperature of minus 80 degrees Fahrenheit, cold certainly, but manageable with current technology. We've operated rovers on Mars for years. We understand how equipment performs in that environment. Titan is more than 200 degrees Fahrenheit colder than Mars. That's not just a quantitative difference, it's a qualitative one. It represents an entirely different category of engineering challenge. Consider your spacesuits. On Titan, you'd actually have an advantage over Mars in one respect. The atmosphere is thick enough that you wouldn't need a pressurized suit. Titan's atmospheric pressure at the surface is about 1.5 times Earth's atmospheric pressure at sea level. You could theoretically wear just a warm coat and oxygen supply rather than a full pressure suit. But that warm coat would need to keep you alive at minus 290 degrees. Any exposure of skin to the atmosphere would result in instant frostbite. Your oxygen supply would need to be heated to prevent it from liquefying. Every breath you take would need to be carefully temperature controlled. One tear in your suit, one malfunction in your heating system, and you'd have seconds, not minutes, before you'd suffer fatal hypothermia. And here's something few people consider. That same cold makes repairing your return vehicle nearly impossible. Imagine trying to work on a spacecraft in these conditions. Your tools would be so cold they'd burn your hands even through insulated gloves. Lubricants would freeze solid. Welds would become brittle. Any repairs to your return vehicle would need to be conducted either in your heated habitat, meaning you'd need to disassemble and bring in components if they even fit, or outside in conditions that make Antarctic winter look balmy. The cold also affects your fuel. The rocket propellants need to be kept at specific temperatures. Some propellants need to be supercooled, others need to be kept warm. Managing propellant temperatures on Titan, where the ambient temperature is already far below the freezing point of most substances, adds yet another layer of complexity to an already impossibly complex mission. Titan's atmosphere is often celebrated as one of its most remarkable features, but for a return mission, it's another formidable obstacle. The atmosphere is incredibly thick, about 4 times denser than Earth's atmosphere at sea level. It's composed primarily of nitrogen, with methane and small amounts of other hydrocarbons. The atmospheric pressure at the surface means your spacecraft won't need a pressure vessel for habitation, which is actually an advantage. But that thick atmosphere creates a perpetual haze that obscures the surface from space. The orange-brown smog is so thick that visible light barely penetrates. When the Cassini spacecraft orbited Saturn and studied Titan, it had to use radar and infrared imaging to map the surface. Even from orbit, you can't see the ground. For landing, this is challenging but manageable. You can use radar and pre-planned coordinates. But for launching, that thick atmosphere becomes a massive problem. Every kilogram of fuel you use just to punch through Titan's atmosphere is a kilogram you can't use for the journey back to Earth. The atmosphere is so thick that you'd need a powerful first stage just to get to orbit, similar to launching from Earth. But remember, you had to bring that first stage with you from Earth, or you had to manufacture it on Titan using local resources, which brings us back to all the problems about resource utilization. The haze also affects solar power even more severely than the distance from the Sun. Even if Titan were closer to the Sun, the thick, smoggy atmosphere would block most of the sunlight from reaching the surface. Solar panels would be almost useless. You're absolutely dependent on nuclear power with no backup option. Distance doesn't just make travel difficult, it makes communication agonizing. Light travels at 186,000 miles per second, the fastest speed possible in our universe. When Titan is closest to Earth, it's still about 746 million miles away. A radio signal traveling at light speed takes about 67 minutes to reach Earth from Titan. When Titan is on the opposite side of Saturn's orbit from Earth, that distance increases to over 1 billion miles, and the signal delay extends to over 90 minutes. This means that any communication with Earth involves a round-trip delay of more than 2 hours. Ask a question, wait 90 minutes for it to reach Earth. Wait for mission control to process your question and formulate a response. Then wait another 90 minutes for the answer to reach you. A simple back-and-forth conversation takes 3 hours minimum. In an emergency, you're on your own. If something breaks, if someone gets injured, if your habitat starts to fail, Earth can't help you in real time. You can't call for advice and get an immediate response. By the time Earth even knows you have a problem, you might already be dead. This communication delay also affects mission planning. Every decision needs to be made autonomously by the crew on Titan. Mission Control can provide guidance, send updates, and review your plans, but they can't actively participate in time-sensitive operations. The psychological weight of this isolation cannot be understated. You're so far from home that even light, the fastest thing in the universe, takes over an hour to bridge the gap. And here's another consideration few people think about. What if something catastrophic happens on Earth? A pandemic? A war? Economic collapse? Political upheaval? Any number of disasters could disrupt the space agencies and private companies supporting your mission. If funding is cut, if mission control is abandoned, if the political will to maintain contact with you evaporates, you'd be completely stranded with no support whatsoever. Not only can't you return physically, but you'd lose even the tenuous electronic connection to humanity. The Mars rovers have occasionally gone into safe mode and waited for instructions from Earth when something unexpected happened. Humans on Titan couldn't afford that luxury. You'd need to be completely self-sufficient, capable of making life or death decisions without input from Earth, and prepared for the possibility that Earth might stop responding altogether. Saturn's magnetosphere, the magnetic bubble that surrounds the planet, creates a harsh radiation environment for its moons. While not as extreme as Jupiter's radiation belts, which are truly lethal, Saturn's magnetosphere still exposes Titan to elevated levels of cosmic radiation and energetic particles. During your journey to Titan, you'd spend years in deep space, beyond the protective bubble of Earth's magnetosphere. Galactic cosmic rays would bombard your spacecraft continuously. These high-energy particles can penetrate spacecraft hulls and even protective shielding, depositing radiation in your body's tissues. Long-term exposure increases your risk of cancer, cataracts, cognitive decline, and other health problems. Once you arrive at Titan, the radiation doesn't stop. Titan's thick atmosphere provides some shielding, far more than the thin atmosphere of Mars. But you'd still be exposed to elevated radiation levels, especially during periods when Saturn's magnetosphere is particularly active. The radiation has another insidious effect. It degrades materials over time. The electronics in your return vehicle, sitting on Titan's surface for years while you prepare for departure, would be slowly damaged by radiation. Computer chips can experience bit flips, random changes to data caused by high-energy particles. Structural materials can become brittle. Your return vehicle essentially has an expiration date. The longer it sits on Titan's surface, the more likely something critical will fail. You can't keep it in orbit to protect it because you don't have the fuel to launch it, keep it in orbit, and then rendezvous with it later. It has to sit on the surface, slowly accumulating radiation damage. For however many years, you need to manufacture enough fuel for the return journey. By the time you're ready to leave, if you ever are, that spacecraft may no longer be space-worthy. Here's a counterintuitive fact. Titan's low gravity actually makes some aspects of a return mission harder, not easier. And Titan's gravity is only about 14% of Earth's, similar to the Moon's gravity. This means launching from Titan's surface requires less energy than launching from Earth, which sounds like good news. However, remember that thick atmosphere we discussed? It creates drag during ascent, partially negating the advantage of low gravity. The real problem with low gravity isn't launching, it's what it does to your body during the years you spend on Titan. We know from decades of research on the International Space Station that microgravity causes serious physiological changes: bone density loss, muscle atrophy, cardiovascular deconditioning, vision problems, and immune system dysfunction. Astronauts returning from 6-month ISS missions can barely stand when they first return to Earth's gravity. They require months of rehabilitation. In Titan's low gravity isn't microgravity, but it's close. Spending years at 14% of Earth's gravity would cause similar problems, perhaps not as severe, but still significant. Your bones would thin, your muscles would weaken, your cardiovascular system would adapt to pumping blood in low gravity, making it struggle when you return to higher gravity. Here's the trap. The longer you stay on Titan, the less capable you become of surviving the return journey. The flight back to Earth involves the same G-forces during launch, course corrections, and landing. Your weakened body might not survive the stress. Even if you make it back to Earth, readapting to full gravity after years at 14% could be impossible. You might spend the rest of your life unable to walk unassisted, your bones too fragile, your muscles too wasted. This creates a cruel deadline. If you're going to return from Titan, you need to do it as quickly as possible, within a year or two maximum, before the physiological damage becomes irreversible. But manufacturing enough fuel for the return journey would take years. By the time your fuel production facility is operational and has generated enough propellant, your body may no longer be capable of surviving the trip home. Let's return to the concept of resource utilization, because it's often presented as the solution to Titan's return problem. The theory is elegant. Use Titan's abundant methane as rocket fuel, eliminating the need to bring all your fuel from Earth. But the devil is in the details. First, you need oxidizer. Methane is a fuel, but it needs oxygen to burn. Titan's atmosphere contains almost no free oxygen. It's locked up in water ice and carbon dioxide. You'd need to extract oxygen from water ice or bring it from Earth. If you bring it from Earth, you're back to the tyranny of the rocket equation. If you extract it on Titan, you need massive industrial equipment. Second, rocket-grade propellants need to be pure. Contaminants can damage engines or cause combustion instability. You'd need sophisticated purification systems to refine Titan's methane into propellant-grade fuel. These systems require power, maintenance, and consumable materials that would eventually run out. Third, you need to liquefy and store your propellants. Methane needs to be kept at minus 161 degrees Celsius to remain liquid. On Titan, where the surface temperature is minus 179 degrees, this is actually easier than on Earth. The environment naturally keeps your methane cold, but oxygen needs to be kept at minus 183 degrees Celsius to remain liquid. You'd need cryogenic storage systems, insulation, cooling systems, and backup power. Any failure in this chain, and your propellants boil off into the atmosphere, and years of work are lost. Fourth, you need enough propellant for the entire return journey. We're not just talking about a few hundred kilograms. Depending on the spacecraft design, you might need dozens of tons of propellant. Manufacturing that much from scratch on an alien world with no resupply from Earth is an industrial undertaking that has never been attempted even remotely close to this scale. And finally, you need all of this infrastructure to work perfectly for years. One breakdown, one contaminated batch, one storage tank failure, and you're set back months or years. The longer the mission takes, the more likely something will fail, and the less likely you'll ever manufacture enough fuel to leave. The resource trap closes tighter. The technology you need to escape requires resources you can only obtain by staying long enough to build industrial infrastructure. But staying that long makes escape increasingly unlikely due to equipment degradation, physiological decline, and psychological stress. Now let's talk about something that mission planners don't like to discuss publicly: the economics of a return mission. Sending humans to Titan would be the most expensive undertaking in human history. The Apollo program, adjusted for inflation, cost about $280 billion. That program sent humans to the moon, which is less than 3 days away from Earth. Titan is years away. A crewed mission to Titan would likely cost trillions of dollars. It would require new heavy-lift rockets larger than anything currently in development, new deep space habitats, new life support systems, new radiation shielding, new propulsion systems, and new everything. The research and development alone would take decades. Here's the uncomfortable truth. From a purely economic perspective, a one-way mission makes more sense. Designing a mission architecture for return doubles or triples the complexity and cost. You need a return vehicle, return propellant, life support for the return journey, and all the redundancy that implies. You need to keep astronauts healthy enough to survive the return trip, which means more medical equipment and supplies. You need to ensure their spacecraft remains functional for years on Titan's surface, which means more spare parts and repair equipment, or, and this is what some mission planners privately acknowledge, you send a one-way mission. The astronauts go to Titan knowing they'll live out their lives there. You send supplies periodically via unmanned cargo missions. You focus on building a permanent settlement rather than a temporary research outpost. The mission becomes about colonization, not exploration. This is psychologically easier to justify if volunteers understand the terms up front. The first Mars colonization proposals from private companies explicitly planned for one-way missions. The logic is straightforward. Removing the requirement to return eliminates the most difficult and expensive parts of the mission. But here's where the trap becomes existential. What government or private company will publicly fund a mission explicitly designed to strand astronauts on Titan forever? The optics are terrible. The ethical questions are profound. The legal liability is enormous. So instead, we'd likely see a mission designed with the theoretical possibility of return, carrying all the equipment for fuel production, packing all the spare parts, maintaining all the redundant systems, but with the quiet understanding among mission planners that return is highly unlikely. The astronauts would be told there's a return plan. The public would be assured that safety is the top priority. But behind closed doors, the spreadsheets would tell a different story. This is the most insidious trap of all. Not a physical trap of distance and fuel, but a social and political trap of expectations and reality. Let's discuss something that engineers and scientists often overlook: the human mind. Imagine you've spent 7 years traveling to Titan. You've left Earth in your 30s. You've watched your friends and family age over video calls with 90-minute delays. You've missed births, deaths, weddings, and life milestones. You've lived in a cramped spacecraft with the same handful of people for 7 years. You finally arrive at Titan. You land successfully. You set up your habitat. You begin the years-long process of manufacturing fuel for the return journey. And then one day, you ask yourself a question. Why? Why go back to a planet you left 7 years ago? A planet where everyone you knew has moved on with their lives? Where you'd be a curiosity, a celebrity for a brief moment, and then a person with no career, no home, no connections, trying to reintegrate into a society that moved forward without you? On Titan, you're essential. You're an explorer, a pioneer, making history every day. You're part of something larger than yourself. The work you're doing matters. What awaits you on Earth? Book deals and talk show appearances for a year, followed by obscurity. A body damaged by years in low gravity. Psychological scars from 2 decades of isolation. An Earth that feels alien after so long away. Some psychologists studying long-duration space missions have identified a phenomenon they call geographic capture, the point at which an explorer becomes more attached to their remote location than to their home. Antarctic researchers sometimes experience this. Deep-sea submariners experience it. Astronauts on the ISS sometimes feel it, even though they're only 250 miles from home. On Titan, years into your mission, you'd face a choice: Spend the next several years manufacturing fuel, preparing your vehicle, keeping yourself healthy enough for the return journey, all for the privilege of spending another 7 years in a cramped spacecraft, traveling back to a world that barely remembers you. Or accept that Titan is your home now. Some crew members would reach this psychological point of no return before others, creating tension and conflict. Those who still want to return would resent those who've given up. Those who've accepted their new home would view the others as delusional, clinging to an impossible fantasy. Mission psychologists understand this risk. They screen candidates for psychological resilience, team compatibility, and adaptability. But there's no way to truly prepare someone for the reality of being a billion miles from home with no realistic hope of return. The mind is remarkably adaptable. It can find meaning and purpose in almost any situation. But that same adaptability means that after years on Titan, the psychological motivation to return may simply evaporate. At that point, the mission becomes a permanent settlement, not because return is physically impossible, but because it's psychologically unbearable. Space exploration has always been as much about politics as science. The Apollo program was driven by Cold War competition with the Soviet Union. The International Space Station exists because of post-Cold War cooperation. Private space companies receive government contracts and favorable regulations. A mission to Titan would require sustained political will over decades. The research, development, construction, launch, and operations would span multiple presidential administrations, congressional sessions, and political climates. History shows that such long-term commitments are difficult to maintain. Consider the Constellation program, NASA's plan to return humans to the Moon, initiated under President George W. Bush in 2004 and cancelled by President Barack Obama in 2010. Consider the Space Shuttle program's multiple near cancellations over its 30-year lifespan. Consider how NASA's budget as a percentage of federal spending has declined from 4.4% during Apollo to less than 0.5% today. Now imagine you're on Titan, years into your mission, dependent on cargo resupply flights from Earth to survive. A new administration takes power on Earth, facing economic crisis or war or pandemic. The space budget gets cut. Cargo missions are delayed or cancelled. Your supplies start running low. This is the political trap. Your mission's success depends not just on technology and physics, but on the continued support of institutions that are fundamentally unstable over the timescales required. Private space companies face similar challenges. They depend on investor funding, which can evaporate if the company isn't profitable or if market conditions change. SpaceX, Blue Origin, and other companies may seem stable now, but corporations collapse all the time. What happens to the Titan mission if the company funding it goes bankrupt? You might think international cooperation would provide stability. No single nation could afford a Titan mission alone, so perhaps a coalition of nations and companies would share the burden. But international cooperation brings its own fragility. Treaties are broken, alliances shift, nations withdraw from agreements. The astronauts on Titan would be acutely aware of this uncertainty. Every political crisis on Earth, every economic downturn, every international dispute would be a potential threat to their survival. And they'd know that if Earth ever decided the mission wasn't worth continuing, there's absolutely nothing they could do about it. They'd be completely at the mercy of political forces billions of miles away. This political vulnerability makes return even less likely. As time passes and public interest wanes, justifying the enormous cost of a return mission becomes politically untenable. It's easier to rebrand the mission as a permanent settlement, to celebrate the astronauts as pioneers, establishing humanity's first permanent home beyond Earth, rather than admit the uncomfortable truth that we abandoned them there. Perhaps the cruelest aspect of the Titan trap is that return isn't completely impossible. It's just improbable. If everything went perfectly, if the fuel production facility worked flawlessly, if no critical equipment failed, if the astronauts remained healthy, if Earth maintained its support, if the return vehicle's degradation was minimal, if the launch succeeded, if the trajectory calculations were precise, if the 7-year journey home proceeded without incident, then yes, return would be possible. This possibility, however remote, would gnaw at you throughout your time on Titan. You'd have to maintain the pretense of preparation, keeping the return vehicle in working order, manufacturing fuel, conducting health regimens, all while suspecting it might be futile. Hope can be a gift, but it can also be a torture device, keeping you working toward a goal you know deep down you'll never achieve. Consider the alternative. If return were truly impossible, if everyone agreed from the start that this was a one-way mission, you could psychologically accept your fate and focus on making Titan your home. You could stop worrying about staying fit for the return journey and accept your body's adaptation to low gravity. You could stop maintaining equipment you'll never use. You could let go. But that slim possibility of return prevents that acceptance. It keeps you in limbo and neither fully committed to Titan as your permanent home, nor realistically able to return to Earth. You're trapped not just physically, but psychologically and emotionally, suspended between two worlds and fully belonging to neither. The engineers and mission planners know this. Some of them argue that false hope is cruel, that honesty about the mission's one-way nature would be kinder. Others contend that hope, even false hope, is necessary for psychological survival. The debate continues in conference rooms and academic papers, but for the astronauts on Titan's surface, the abstract ethical discussion becomes a lived reality. Let's consider the medical challenges in more detail, because they compound every other problem we've discussed. A mission to Titan would need comprehensive medical facilities, far beyond what the ISS provides. You'd need diagnostic equipment, surgical capabilities, pharmaceutical supplies, and the ability to handle everything from minor injuries to life-threatening emergencies. But medical supplies have expiration dates. Medications degrade over time, especially under radiation exposure. Sterile equipment can become contaminated. Diagnostic machines require calibration and maintenance. And unlike on Earth, you can't just order replacement supplies or call in a specialist. Imagine a crew member develops appendicitis 5 years into the mission. On Earth, this is a routine surgery with minimal risk. On Titan, it's a life-threatening emergency. The crew's medical officer, trained in emergency procedures, but not a surgeon by specialty, would need to perform the operation with whatever equipment and supplies remain functional. There's no anesthesiologist, no surgical team, no backup if something goes wrong. The patient either survives or doesn't, and if they don't, the rest of the crew must live with that loss for the remainder of their time on Titan. Dental problems present their own challenges. A simple toothache on Earth is treated with a quick visit to the dentist. On Titan, dental infections can become life-threatening if untreated. The crew would need dental equipment, training in basic dentistry, and enough supplies to handle years of potential problems. Tooth extractions, root canals, filling cavities, all of these procedures would need to be performed by crew members with limited training and no ability to consult with specialists in real time. Mental health is another critical concern. The isolation, stress, and awareness of being trapped would inevitably take a psychological toll. Some crew members might develop depression, anxiety, or other mental health conditions. On Earth, these conditions are treated with therapy and medication. On Titan, your therapist is billions of miles away with a 2-hour communication delay. Psychiatric medications can help, but they also have expiration dates and potential side effects that could be dangerous in such an isolated environment. And what about injuries? A broken bone, a severe burn, a head trauma. These are survivable on Earth with proper medical care. On Titan, they could easily be fatal. The low gravity might actually make some injuries worse, as bones that don't bear regular weight load become more fragile. The radiation exposure increases cancer risk, and if someone develops cancer, the treatment options would be severely limited or non-existent. This medical vulnerability creates another dimension of the trap. The longer you stay on Titan, the more likely someone will develop a serious medical condition. But returning to Earth for treatment isn't an option. You're stuck managing whatever health crises emerge with whatever resources you have, watching helplessly as conditions that would be treatable on Earth become chronic or fatal on Titan. The equipment you bring to Titan has a limited lifespan. Every machine, every tool, every component will eventually wear out or break down. On Earth, maintenance and repair are straightforward. You order replacement parts, call a technician, or upgrade to newer equipment. On Titan, you have only what you brought with you and whatever you can manufacture from local resources. The 3D printing is often cited as a solution. Bring a 3D printer and raw materials, and you can manufacture replacement parts as needed. This sounds elegant in theory, but the reality is more complicated. 3D printers themselves require maintenance and have components that wear out. The raw materials, whether plastic filaments or metal powders, have finite supplies. And not everything can be 3D printed. Complex electronics, precision optics, and specialized sensors require manufacturing capabilities far beyond what a 3D printer can provide. Your habitat's life support system is the most critical equipment, and it's also complex with numerous failure points. Air recyclers, water purification systems, temperature control, pressure regulation, all of these systems must function continuously. A single major failure could make your habitat uninhabitable within hours. Redundancy is the standard solution. Bring backup systems, backup components, backup backups. But redundancy adds weight, which adds cost, which makes the mission less feasible. And eventually, even redundant systems fail. If you're on Titan for 10 years, 15 years, 20 years, systems designed for 5-year lifespans will fail multiple times. Each failure consumes spare parts. Each repair risks introducing new problems. The return vehicle faces the same challenges but worse. It sits unused on Titan's surface for years, exposed to radiation, temperature fluctuations, and the corrosive effects of Titan's atmosphere. The methane and ethane lakes might seem romantic, but these hydrocarbons can degrade certain materials over time. Seals dry out. Lubricants break down. Electronic components degrade. When the time finally comes to use the return vehicle, assuming you've manufactured enough fuel, you'd be launching in a spacecraft that's been sitting dormant for years in a harsh environment. Every system would need to be checked and tested. But how do you fully test a spacecraft on Titan? You can't exactly take it for a test flight. You'd be betting your lives on equipment that hasn't been used in years, trusting that everything still works as designed. The engineering trap closes in. The longer you stay, the less reliable your equipment becomes. But you must stay long enough to manufacture fuel for return. By the time you have the fuel, your return vehicle may no longer be trustworthy. Do you risk the launch knowing the vehicle might fail? Or do you accept that the window for return has closed? Titan's environment presents challenges that go beyond cold and radiation. The Moon's atmosphere contains complex organic chemistry with hydrocarbons that don't exist naturally on Earth. These compounds create a thick haze that gives Titan its distinctive orange color, but they also present potential hazards. Some of these organic compounds are toxic. Others might be corrosive to certain materials. We don't fully understand how all of Titan's atmospheric chemistry works because we've never had humans there to test it. The Cassini-Huygens mission provided valuable data, but it couldn't predict every possible interaction between human technology and Titan's environment. What if your habitat seals begin to degrade after prolonged exposure to Titan's atmosphere? What if certain materials you're using for equipment or spacesuits break down faster than expected? These are questions that can only be answered by actually being there, and the answers might be unpleasant surprises. The methane and ethane lakes present another category of challenge. Liquid hydrocarbons are chemically quite different from water. If your equipment comes into contact with these liquids, perhaps during exploration or resource extraction, how will it react? Will seals hold? Will electronics survive? Will spacecraft surfaces corrode? We've landed rovers in Martian dirt and had them function for years. We've never immersed sophisticated equipment in liquid methane at -179 degrees Celsius. The first humans on Titan would essentially be conducting these experiments in real time, with their lives depending on the results. And there's another consideration. Titan might have subsurface oceans of liquid water, heated by tidal forces and radioactive decay. If such oceans exist, they could potentially harbour life. This is scientifically exciting, but operationally complicated. Contamination protocols would require extreme caution to avoid introducing Earth microbes to Titan's potential biosphere. But these same protocols would make resource extraction and industrial operations more difficult. Imagine trying to drill for water necessary for oxygen production and life support, while simultaneously ensuring you don't contaminate a potential subsurface ocean. The equipment would need to be sterile. The procedures would need to be meticulous. Any shortcuts could violate international planetary protection agreements and potentially harm an alien ecosystem. But taking the time to do everything properly extends your timeline, consumes resources, and makes return even less likely. The environmental trap is one of unknown unknowns. You can plan for known challenges, but Titan will inevitably present surprises. Some of these surprises might be manageable, others could be mission-ending, and you won't know which until you're already there, billions of miles from help. Let's talk about food, because it's easy to overlook but absolutely critical. The International Space Station is resupplied every few months with fresh food and supplies. Astronauts eat a variety of freeze-dried, thermostabilized, and vacuum-packed foods, supplemented occasionally with fresh fruit and vegetables from resupply missions. On Titan, resupply missions would arrive years apart at best. Each cargo mission from Earth to Titan takes 7 to 10 years. By the time you realize you're running low on a critical supply, it's far too late to request more. You'd need to bring enough food for the entire mission, plus substantial reserves for emergencies. But food degrades over time. Even freeze-dried and vacuum-sealed foods eventually lose nutritional value. Vitamins break down, flavors fade, textures change. After several years, your carefully packed provisions might become unpalatable or nutritionally insufficient. This is where hydroponics and food production become essential. Growing food on Titan would provide fresh produce, supplement your diet, and give crew members a psychologically valuable activity. Plants also help with air recycling, consuming carbon dioxide and producing oxygen. But growing food requires resources that are precious on Titan. Water, which you'd need to extract from ice and carefully recycle. Energy for lighting, since Titan's surface is far too dim for natural photosynthesis. Temperature control, since plants can't survive at -179 degrees. Growth medium or soil, which you'd need to bring or manufacture. And space, since a hydroponic system large enough to significantly supplement a crew's diet takes up substantial room in your habitat. Plant diseases and pests are another concern. If a pathogen or insect contaminates your hydroponic system, it could devastate your food supply. On Earth, you could get new seeds or start over. On Titan, losing your crop could mean the difference between adequate nutrition and slow starvation. And here's something even more subtle. The psychological importance of food cannot be overstated. Meals are social occasions, sources of comfort, connections to home and culture. Eating the same freeze-dried packets day after day for years wears on your mental health. The ability to occasionally eat something fresh, something different, something with actual flavor and texture becomes critically important for morale. If your hydroponic system fails, if your food supplies degrade faster than expected, if you miscalculated your nutritional needs, you face a slow crisis. Unlike a sudden emergency like habitat breach, food shortages creep up gradually. You start rationing, you extend the time between meals, you accept that you're always slightly hungry. And all the while, you know there's no resupply coming. Is no way to get more food except to grow it yourselves or wait years for a cargo mission that might never arrive. The food trap is insidious because it seems so mundane. Surely professional mission planners would bring enough food. Surely the systems would be redundant. But when you're looking at a mission lasting 15 or 20 years with no realistic possibility of resupply, even small miscalculations become fatal. Now consider the social dynamics of a small crew isolated for years or decades. You're living in extremely close quarters with the same handful of people, perhaps only 4 to 8 crew members total. You can't get away from them. You can't take a vacation. You can't quit and go home. Whatever interpersonal conflicts emerge must be resolved, or they'll fester and poison the entire mission. History shows that isolation and confinement breed conflict. Antarctic research stations have experienced fights, social fragmentation, and psychological breakdowns. Submarine crews develop strict hierarchies and social rules to maintain order. Even on the ISS, with its relatively short mission durations and regular crew rotations, tensions arise. On Titan, there's no crew rotation. The people you launch with are the people you'll live with for the rest of your time there. If you develop a personality conflict with someone, you can't transfer to a different station. If someone's habits or behaviors become unbearable, you can't avoid them. The habitat is too small, the mission too long. Romantic relationships add another layer of complexity. If crew members become romantically involved, what happens if the relationship ends badly? If jealousies develop, if love triangles emerge, if breakups occur, these personal dramas play out in an environment where the participants can't escape each other. And if a pregnancy occurs, the mission suddenly has a much more complicated situation to manage. Mission planners try to mitigate these risks through careful crew selection, psychological screening, and training in conflict resolution. But no amount of screening can predict how people will actually behave after 5 years on Titan. Personality traits that seemed minor on Earth might become intolerable in close confinement. Stress and isolation can bring out the worst in people. And there's a darker possibility. What if serious conflict erupts? What if violence occurs? On Earth, we have police, courts, and prisons to handle violent crime. On Titan, you're your own police force. If a crew member becomes violent, mentally unstable, or poses a danger to others, what do? Restrain them? Confine them? These are questions that mission planners desperately hope never need answers, but the isolation and stress of Titan make such scenarios disturbingly plausible. The social trap is that humans are deeply social creatures, but we're also territorial and prone to conflict. Put a small group in isolation for long enough, and tensions will emerge. Whether those tensions remain manageable or explode into something destructive depends on factors that are hard to predict and impossible to control once you're already on Titan. Let's address something we've been dancing around. Death on Titan is not an if, but a when. Statistically, with a small crew over a period of many years, someone will die. It might be an accident, a medical emergency, equipment failure, or simply age and accumulated health problems from the harsh environment. When someone dies on Earth, we have established procedures: funerals, burials or cremations, grieving rituals, support systems for those left behind. On Titan, the remaining crew must handle death alone. There's no morgue, no funeral home, no grief counsellor except each other. You must decide what to do with the body. Burial in Titan's frozen surface, cremation, which requires fuel and energy, storage, which requires space and preservation, and you must continue living and working in the same small habitat where someone died. That habitat becomes a tomb, a memorial, a constant reminder of loss. There's no moving to a new house, no change of scenery. You're stuck there with your grief and your memories, for years or decades more. Multiple deaths compound the trauma. If the mission lasts 20 years with a crew of 6, probability suggests you might lose half the crew to various causes. The survivors would be living in a habitat haunted by the ghosts of lost colleagues and friends. The psychological toll would be enormous. And here's the cruelest possibility. What if you're the last one left? What if everyone else has died and you're alone on Titan, billions of miles from any other living human? You'd have all the systems of a multi-person habitat to maintain by yourself. You'd have no one to talk to except Earth with its 90-minute signal delay. You'd be facing the rest of your life in complete isolation, knowing you'll eventually die alone on an alien world. This scenario isn't far-fetched. Accidents, illness, and the cumulative effects of radiation and low gravity make mortality rates on Titan far higher than on Earth. Mission planners don't like to discuss these probabilities publicly, but actuarial tables don't lie. The longer the mission, the fewer crew members, the harsher the environment, the more likely that some or all will die before any possibility of return. The mortality trap is the ultimate manifestation of all the other traps. It's the endpoint toward which all the other problems inevitably lead. And knowing this, intellectually understanding that you're likely going to die on Titan, creates a psychological burden that's hard to articulate. Some might find peace in it, accepting their fate and making the most of their time. Others might be consumed by regret, anger, or despair. There's one more dimension of the trap we need to address: the knowledge trap. The first humans on Titan will learn things no one else knows. They'll make discoveries about Titan's geology, chemistry, atmosphere, and potentially even biology. This knowledge is valuable to humanity, advancing our understanding of the solar system and possibly answering profound questions about life in the universe. But what good is knowledge if it dies with you? Communication with Earth is limited by bandwidth and signal delay. You can transmit data, photos, and reports, but there's only so much you can send. Complex scientific insights, subtle observations, the accumulated expertise of years of living on Titan, much of this tacit knowledge can't be easily transmitted. It exists in your mind, in your experiences, in your intuitive understanding of Titan's environment. If you never return, all of that knowledge dies with you on Titan. Future missions, if they ever happen, will need to relearn many of the same lessons. Your hard-won expertise, purchased at the cost of years of your life, becomes lost knowledge, recorded perhaps in logs and reports, but lacking the depth that comes from direct transmission between humans. This creates a tragic irony. The mission to Titan is justified on scientific grounds, the pursuit of knowledge, yet the circumstances that make the mission possible also make it likely that much of that knowledge will be lost. The scientists who go to Titan will die before they can fully share what they've learned, their discoveries partially transmitted but never fully realized. In the final analysis, the trap that ensnares the first humans on Titan is not a single mechanism, but a convergence of multiple traps. The fuel trap, the distance trap, the equipment trap, the medical trap, the social trap, the psychological trap, the political trap, the economic trap, they all interlock, each reinforcing the others, creating a situation from which escape becomes progressively more unlikely the longer you remain. This is why Titan may be humanity's most beautiful prison. It's a fascinating world, rich with scientific potential, tantalizingly similar to Earth in some ways, yet utterly alien in others. It calls to us, promising discoveries and adventure. But it's also incredibly hostile to human life, incredibly far from Earth, and incredibly difficult to leave once you arrive. The first humans who set foot on Titan will be pioneers in the truest sense, venturing into an environment from which there may be no return. They'll need to be not just scientists and engineers, but also philosophers who've made peace with their probable fate. They'll need to find meaning not in returning home as heroes, but in the work itself, in the daily routine of survival and discovery on an alien world. Perhaps they'll never return to Earth. Perhaps they'll live out their remaining years beneath Saturn's rings, watching the massive planet drift across Titan's orange sky, knowing that they're the first and possibly the last humans to ever call this distant moon home. Perhaps future historians will look back on them as tragic figures, heroes who sacrificed everything for knowledge, or perhaps as the vanguard of humanity's expansion into the outer solar system, the first citizens of a new world. One thing is certain. Once you land on Titan, you step into a trap that has been millions of years in the making, forged by the fundamental laws of physics, by the vast emptiness of space, by the limitations of human technology and human physiology. You become part of Titan in a way that's profound and irreversible, bound to that world not by choice, but by the simple mathematics of distance, fuel, and time. The first humans on Titan will never return, not because return is absolutely impossible, but because the convergence of obstacles makes it so improbable that it amounts to the same thing. They'll be trapped not by malice or by mistake, but by the sheer difficulty of moving humans across the solar system and bringing them back home. They'll be explorers, scientists, martyrs, and exiles living out humanity's grandest adventure while simultaneously experiencing its greatest isolation. And perhaps that's the most sobering lesson of all. As we look outward to the stars, dreaming of colonies on other worlds and humanity's expansion across the cosmos, we must confront the reality that space exploration at these distances might not be about round trips. It might be about one-way journeys to places we'll never leave, about saying goodbye to Earth forever, about accepting that some destinations are so remote, so challenging, that reaching them means never coming home. Titan is the first of these destinations, but it won't be the last. The trap awaits anyone who dreams of touching the outer solar system, beautiful and terrible and inescapable, just like the orange haze that hangs forever over Titan's frozen surface.